Imagine you have a superpower to move things without touching them. That's essentially what electric and magnetic forces do. These two are known as non-contact forces, meaning they can push things away or pull things closer even when there's a distance between them. These amazing forces are everywhere, and they are both caused by things you can't see: electric charges in atoms and the motion of those charges. We are going to explore how they work and how we can experiment with them. To understand electric forces, you have to think small, really small, down to the atoms that make up everything. Atoms have two main types of charge: positive and negative. You can think of positive charges like one team in a tug of war, and negative charges like the other. In most everyday objects, these two teams are perfectly balanced, so the object is neutral. It only becomes interesting when we mess with that balance. Electric charges follow one of the most important rules in science: opposites attract. A positive charge is always pulling toward a negative charge. It's like when you meet someone who is totally different from you and you get along great. But if you put two positive charges together or two negative charges together, they repel or push each other away. This simple rule of attraction and repulsion is the basis for every electric force we observe. The most common way we see electric force is through static electricity. Ever rubbed a balloon on your head and watched your hair stick up? That's static charge. When you rub two materials together, you are actually rubbing off some of the tiny negative charges, called electrons, from one object onto the other. This creates an imbalance. The object that gained electrons becomes negatively charged, and the object that lost them becomes positively charged. This is a fun experiment you can easily do at home. Take a balloon and rub it back and forth on your hair for about 10 seconds. When you bring the balloon close to your hair, it stands straight up because the hair and the balloon now have opposite charges and are attracting each other. You can even stick that balloon to a wall. The negative charges on the balloon attract the positive charges in the wall's surface, causing a small temporary attraction strong enough to hold the balloon in place. Now let's switch to the second force, magnetism. Magnetic force is the push or pull that comes from magnets, and just like electricity, it's a non-contact force. But unlike electric charge, which is found in all matter, magnetism only strongly affects a few special materials, primarily iron. Every magnet creates an invisible area around it, called a magnetic field. If you sprinkle iron filings near a magnet, you can actually see the shape of that invisible field. If you look at any magnet, you'll see it has two defined spots where the force is the strongest, and we call these the poles. Every magnet has a north pole and a south pole, and you can't have one without the other. It's always a pair. If you could cut a magnet exactly in half, you wouldn't get a separate north and south piece. You'd just end up with two smaller magnets, each with its own north and south poles. Just like electric charges, magnetic poles follow the opposites attract rule. If you bring a north pole close to a south pole, they instantly pull toward each other. Try it with two refrigerator magnets. They snap together. But if you try to push two north poles together, or two south poles, you'll feel a strong force of repulsion pushing them apart. You can feel this invisible force resisting your hand, demonstrating that magnetic force is very real. A great way to investigate magnetism is by mapping the magnetic field. You can take a small compass and move it around a bar magnet placed on a sheet of paper. Watch the compass needle. It's actually a tiny magnet itself. It will always align with the field lines created by the bar magnet. By drawing dots where the needle points and connecting them, you can physically trace the invisible lines of force that make up the magnetic field. It's a wonderful way to visualize a hidden force. While magnets are fun, they don't attract everything. Why don't they stick to plastic or wood? Only a few materials are strongly magnetic. The big three are iron, nickel, and cobalt. That's why things like paper clips, steel tools, and many kitchen utensils stick to magnets. They contain iron. If an object doesn't have these elements, the magnetic force simply doesn't have enough material to latch onto. You might not realize it, but the Earth itself is a gigantic magnet. Deep inside the planet, the liquid iron in the core is constantly moving. This motion acts like a giant natural electric current, generating a massive magnetic field that wraps around the entire planet. This field, called the magnetosphere, is incredibly important because it acts as a shield, deflecting harmful energetic particles coming from the sun. Without it, life on Earth would be very different. That Earth-sized magnetic field is exactly how a compass works. A compass needle is just a lightweight, freely moving magnet. Since opposite poles attract, the compass needle's north pole is attracted to the Earth's magnetic south pole, which is near the Earth's geographic north pole. The needle simply aligns itself with the invisible magnetic field lines that stretch all around the globe, giving sailors and hikers a way to navigate. For centuries, people thought electricity and magnetism were completely separate. Then, scientists discovered the amazing link: electromagnetism. The core idea is simple. Anytime an electric charge moves, it creates a magnetic field. Think of it like this: electric current is the source, and a magnetic field is the result. This discovery was revolutionary because it showed that these two forces were actually two sides of the same electromagnetic coin. The most direct way to prove electromagnetism is to build an electromagnet. You take a simple piece of iron, like a nail, wrap it tightly with insulated wire, and then connect the wire to a battery. The electric current flowing through the wire creates a strong magnetic field in the coil. Because the wire is wrapped around the iron core, the nail itself becomes a powerful temporary magnet that can pick up paper clips. As soon as you disconnect the battery, the magnetism instantly vanishes. Electromagnets are perfect for investigation because we can easily change their strength. In the lab, you can test 3 different variables. First, the number of coils. Wrapping the wire more times makes the magnetic field stronger. Second, the amount of current. Adding more batteries means more current, which makes the magnet stronger. And finally, the core material. Using iron makes the magnetic field much stronger than using wood or plastic. The ability to turn a magnetic force on and off makes electromagnets incredibly useful in industry. Think about junkyards. Massive electromagnets on cranes can lift entire cars or huge piles of scrap metal. They grab the metal, move it where it needs to go, and then with the flip of a switch, the power is cut and the metal instantly drops. They are also used in recycling plants to magnetically sort iron and steel from non-magnetic trash. One of the most common and important applications of electromagnetism is the electric motor. Motors use the principle of attraction and repulsion to create rotational motion. An electric current flows into coils of wire, creating a temporary magnetic field. This field then pushes against the fields of permanent magnets inside the motor. This continuous push and pull causes the coils to spin, which is the force that turns your fan, blends your smoothie, or even moves an electric car. Here's a futuristic application: maglev trains. Maglev stands for magnetic levitation. These super-fast trains use powerful electromagnets to create strong magnetic repulsion, which is the like poles pushing each other away. This force lifts the train several inches off the track. By floating, the train completely eliminates friction, allowing it to move incredibly smoothly and reach speeds much higher than conventional wheeled trains. So how are these two forces related? They share many similarities. Both are non-contact, and both follow the rule that opposites attract and likes repel. But they have some key differences too. Electric force comes from tiny charged particles. protons, and electrons, and affects all matter. Magnetic force comes from poles and primarily affects only materials like iron, nickel, and cobalt. They are fundamentally linked, but their effects are slightly different. To wrap up, electric and magnetic forces are two sides of the same phenomenon, electromagnetism. This invisible, powerful force is all around us, keeping our planet safe, allowing us to navigate, powering our technology, and even creating the motors that run modern life. By conducting investigations, you learn to see the rules of attraction and repulsion at work, giving you the power to understand and even harness one of nature's fundamental forces.